Welcome to the Deep Dive. This is where we take the source material you share with us and, well, we really dig in, try to pull out the most important bits of knowledge or insight. Today we're tackling a really fascinating research paper you sent over, all about something called V JEPA 2.
That's right. And our mission here, our goal for this deep dive is pretty clear. We want to unpack this specific research, really get what the V JEPA 2 model is all about.
Right.
And maybe most importantly, explore what it could mean. Its implications for the future of AI.
Especially, it seems, how AI learns to understand the world and predict it, interact with it.
Exactly. That whole physical world understanding piece.
Okay, so think of us as your guides, just trying to help you navigate this paper and see what's really key inside.
Let's jump right in. Maybe start with the big problem V JEPA 2 is trying to solve.
Okay, yeah. What's the fundamental challenge here for AI?
Well, it's this really core difficulty that modern AI systems have. Learning how the world works and then, crucially, being able to act in that world.
Just by watching? Like we do?
Primarily by observation, yeah. I mean, think about humans. We watch things, we interact a bit, and we build this internal model of reality. We use it constantly to predict what's going to happen next, to plan our actions.
Right. You see a glass near the edge of a table, you kind of instinctively know what happens if it gets nudged. You don't need like a physics degree.
Exactly. And cognitive science theories have talked about this for ages. We integrate all our senses, sight, sound, touch, to build this model and predict future states.
And that predictive ability is key for planning, right? Knowing if I do X, then Y will likely happen.
Absolutely crucial. It's fundamental to intelligent behavior.
So, okay, how does this V JEPA 2 paper, how does the research team try to get AI to learn like that?
Their main tool is self-supervised learning. They train the model on just massive amounts of online video, a ton of it.
Just watching.
Watching, mostly. And then they combine that with a comparatively small amount of interaction data, like videos of robots moving and doing things.
So it's like letting the AI binge watch the world first, get a general sense, and then give it some hands-on or maybe gripper-on experience.
That's a good way to put it, yeah. And the core technical idea here is GPP, the Joint Embedding Predictive Architecture. This concept, pushed by Yann LeCun, it's clever.
How so?
The big idea isn't to predict future video frames pixel by pixel.
Which seems insanely hard, like predicting every single raindrop in the next frame.
Exactly. And maybe not even that useful, right?
Yeah.
It's computationally brutal, and you get bogged down in predicting totally unpredictable details. Noise, essentially.
Like the exact way a leaf flutters.
Precisely. Instead, GP learns by making predictions in a learned representation space, an abstract space.
Okay, unpack that a bit. Representation space.
Think of it like the model learns a more abstract understanding, a sort of conceptual summary of the video. Then it predicts what that summary will look like in the future.
So it predicts the predictable things, maybe an object's general path, but ignores the unpredictable details, the visual noise.
You got it. It focuses on the underlying dynamics, like predicting the car will continue moving forward rather than predicting the exact reflection on its window.
That makes sense. Seems more efficient, more robust, maybe.
That's the argument. More efficient and potentially better at capturing the actual physics or semantics of what's happening.
Got it. So how did they actually build and train this V JEPA 2 model? What were the steps?
It was a two-stage process.
Okay. Stage one.
Stage one was the big pre-training phase for V JEPA 2 itself. Here, they trained the core model, which doesn't know about actions yet, just on video.
And this is where the massive data set comes in.
Oh, yeah. Over 1 million hours of internet video. They specifically mentioned the VM22M data set. That's 22 million videos.
22 million. That's just staggering.
It really is. And the paper points out a few key things that made this V JEPA 2 possible, things they scaled up massively compared to earlier work.
Like what?
Well, the data, obviously 22 million videos, but also the model size. They used a huge fission transformer, VITG, up to 1 billion parameters.
1 billion. Okay.
And they trained it for much longer, up to 252,000 iterations. Plus, they used higher resolution video, training progressively up to 384 by 384 pixels, 64 frames long. These scaling ingredients, as they call them, were crucial.
So bigger model, way more data, longer training, higher resolution. The usual suspects for deep learning success, but pushed really far here.
Pretty much. It's that large-scale approach.
And during this massive video watching phase, What's the model actually learning to do? What's the task?
The objective is called mask denoising in representation space.
Okay.
Imagine you show the model part of a video, but you blank out or mask another part, say the middle or the end.
Right.
The model's job is to predict the representation, the abstract summary of the part it can't see. It has to fill in the conceptual blank based on the context.
Ah, I see. So by learning to predict the missing meaning of video segments, it builds this internal, coherent understanding of how visual scenes evolve.
That's the intuition. It learns the structure and dynamics implicitly.
Okay, that's stage 1, huge observation phase. What's stage 2?
Stage 2 is where they bring in actions. This is the VGP2AC post-training. AC for action conditioned.
Right.
They take that powerful VGP2 encoder, the part that understands video representations from stage 1, and they freeze its weights. They don't change it anymore.
Okay, lock in that visual understanding.
Exactly. Then they train a new, smaller model on top of it. This is the VGP2AC model, and this one is conditioned on actions.
And this uses the interaction data you mentioned, the robot videos.
Yes, but here's the kicker. They used a surprisingly small amount, less than 62 hours of unlabeled robot video from a dataset called Droid.
Wow, less than 62 hours compared to over 1 million hours of internet video. That's a tiny fraction.
Tiny. And unlabeled, meaning no one told the model this action achieves this specific goal. It just saw robot arms moving, pushing things, etc., along with the corresponding actions being taken.
So what does this VGP2AC model learn to predict?
It learns to predict the representation of the next video frame, given the representation of the previous frames and the action that was taken.
Okay, so stage 1, learn general world dynamics by watching everything. Stage 2, learn specific action consequences by watching a little bit of interaction, layering that onto the general knowledge.
You've got it. And the results they show are, well, pretty compelling across different capabilities.
Let's get into that. VJEPA2 in action. How well does it actually understand the physical world after all that watching?
The pre-trained VJEPA2, even before stage 2, shows really strong signs of understanding. On tasks judging motion understanding, like the something V2 benchmark.
That's the one with short clips like pushing something so it falls off?
Yeah, exactly. Requires understanding cause and effect from motion. VJEPA2 got 77.3% top 1 accuracy there, which is very good. It shows it's encoding fine-grained motion well.
Okay, that's understanding motion. But then they did something even more interesting, combining it with a language model.
Right. This is where it gets really cool, I think. They took the VJEPA2 encoder and essentially connected it or aligned it with a large language model, an 8 billion parameter one.
To do what?
To enable video question answering, or VidQA. Basically, ask the model questions about a video in natural language.
And how to do?
State-of-the-art results on several benchmarks that specifically test physical world understanding and reasoning over time. They mentioned perception test, where it got 84.0%, and temp compass at 76.9%. Really strong scores.
But wait, the really surprising part you flagged from the paper, VJEPA2 itself wasn't trained on any language, right? Just video pixels, essentially.
None at all during the pre-training. It learned purely from visual data. Yet, when they aligned it with the LLM and they mentioned scaling up this alignment data, using up to 88.5 million image-text pairs was important.
Okay.
It could suddenly leverage its visual understanding to answer complex language-based questions about physics, causality, and timing in videos. It's a great example of grounding language in visual understanding.
That is surprising. Okay, so it understands things well. What about predicting the future? How did it fare there?
Also very strong. They tested it on human action anticipation using the Epic Kitchens 100 dataset.
Predicting what someone's about to do next in a kitchen, like grabbing a knife before they start chopping.
Exactly that kind of task. And it achieved a new state-of-the-art result. 39.7% recall at 5.
How good is that compared to what came before?
The paper notes it's a 44% relative improvement over the previous best model. And the previous best was Plausiviel, which itself was a powerful 8 billion parameter LLM-based approach.
Wow, so this video-based world model is significantly better at predicting future actions than even large language models trying the same task.
It seems so, based on this benchmark. And again, they saw that performance scaled up with the VJEPA2 model size and the resolution it was trained on. Bigger and clearer inputs led to better predictions.
Okay, understanding, check. Prediction.check. Now, the part that really jumped out at me, the planning, using this for actual robot control.
Yeah, this is arguably the most exciting demonstration in the paper.
Yeah.
They deployed the VJEPA2AC model, the action condition one, directly onto real Franco robot arms.
And crucially, they did it zero shot. What does that mean in this context?
It means they put the model onto robots in two completely different lab environments that the model had never seen any data from during its training. None at all.
So new lighting, new tables, new robot setup.
Totally new.
Yeah.
And critically, no task-specific fine-tuning for those labs. No rewards telling it good job or bad job for that specific pick-and-place task in that room. They just deployed it.
That's a serious test. Did it have a generalized enough world model to actually work?
That was the question. The task was to get the robot to pick up objects and place them somewhere else, guided only by a goal image.
So you show it a picture of, I want the red block over here, and it has to figure out the moves.
Exactly, just the goal image.
And how does it use its world model, the VGP2AC part, to figure that out?
It uses a planning technique called Model Predictive Control, or MPC.
Okay.
Basically, the robot constantly uses VGP2AC to simulate, if I try this sequence of moves, what will the world look like according to my model? It imagines the future in that abstract representation space.
Not generating pixels, but predicting the future representation.
Right. And it plans by finding the sequence of actions that its model predicts will result in a future representation closest to the representation of the goal image you gave it.
So it's mentally rehearsing in its learned abstract space.
Kind of, yeah. It picks the best-looking plan, executes the first action, then observes the world again and replans from the new state, constantly predicting and adjusting.
Super interesting. And the results? On the real robots, 0 shot.
For being dropped into unseen environments with no specific training, they were really quite good. 100% success on just reaching for a target location.
Okay, reaching is one thing. What about actually manipulating objects?
For grasping an object, they reported a 65% average success rate. And for the full pick-and-place task, also a 65% average success rate.
65% isn't perfect, but for 0 shot in a new lab. That's pretty impressive, actually.
It really is. It shows the model learned something general enough about interaction to be useful immediately. And they highlighted the efficiency, too.
Right, you mentioned that earlier, compared to models that generate video.
Yeah, they compared planning with VGP2AC against a video generation model called Cosmos. VGP2AC took about 16 seconds to plan each action using 800 simulated rollouts.
Okay.
Cosmos took 4 minutes per action with only 80 rollouts and still performed worse on the task. Planning in representation space is just way, way faster.
Which is critical if you want a robot to do anything in reasonable time.
Absolutely. 4 minutes per move isn't practical.
Okay, so let's pull back. We've seen understanding, prediction, even 0 shot robot planning. What's the big picture here? What are the major implications of this VGP2 work?
Well, I think it's a really significant step. It's moving towards AI systems that don't just, recognize patterns in data, but actually build an internal model of the physical world.
A model they can use to understand, predict, and plan.
Exactly. And crucially, do that effectively, even in new situations they haven't explicitly trained for. That 0-shot robot result is key.
And it really seems to validate this approach of massive self-supervised learning from observation, just watching videos, combined with a much smaller dose of interaction data?
Yes, that seems to be a powerful recipe. It suggests you might not need enormous data sets of robots performing every single task you want them to learn.
Which is often the bottleneck, right? Getting that kind of specific, labeled interaction data is hard and expensive.
Very hard. So this offers a potential alternative, or at least a strong complement. Learn the general physics from cheap, abundant video, then specialize with a little interaction.
It feels like a shift towards more generalist AI agents. Systems that learn foundational models of the world from sensory input, maybe a bit more like how humans or animals learn.
That's definitely the direction it points, moving away from narrow, task-specific models towards broader world understanding.
Now, the paper was honest about limitations too, wasn't it?
Yes, absolutely. For the robot control, they noted it was somewhat sensitive to the exact camera positioning.
Which makes sense if it's learning implicitly from pixels without, say, explicit 3D calibration data.
Right. And the classic problem for any kind of long-term planning, error accumulation. Small prediction errors can build up over a long sequence of actions.
Makes sense. Any other future directions mentioned?
They explicitly point to scaling even further. Given the trend, they saw better performance with bigger models and more data up to the 1 billion parameter scale they suggest. Pushing beyond that is a promising next step.
No surprise there, I guess. Scaling seems to be the magic ingredient often.
It often helps, yes.
Okay, so wrapping this deep dive up, the key takeaway seems to be that V JEPA 2 really demonstrates the power of these self-supervised world models, learning from tons of observation, a bit of interaction.
Allows AI to achieve state-of-the-art performance in understanding, predicting, and even planning complex actions like robot manipulation, zero-shot, in the real world.
It really shows why digging into sources like this paper is so valuable. You find these glimpses of potentially transformative approaches. So here's a final thought for you, the listener, to chew on. This work suggests AI can learn a model of reality much like we do by simply watching the world. How far could such observational learning really take us in building truly intelligent agents?
That's the billion-dollar question, isn't it?
It certainly is. Thank you for sharing your source material for this deep dive. We hope this exploration of V JEPA 2 gave you some valuable insights.